for our questions about modeling exponential growth and exponential decay. So we'll start with question 1. What do we got here? So we got a population of bacteria that doubles every 2 hours. So I'm going to grab some highlighters here. Okay, so the bacterial colony doubles every 2 hours. And we know that the population is 180 at 9 a.m. And the question is, what will be the population at 4 p.m. 4 p.m. the next day? Okay. So, as we've been doing before, we're going to start by labeling all of our variables. Our y, our a, our b, our t, and our d. So this y represents our final value. This will be our final population. And I'm going to call it p of t. I like to change it into function notation. You could also just call it p, or you could also just keep it as y if you prefer. There's nothing wrong with doing that. Our initial value, our initial population. I think I'll take my time on this first one, writing out my thoughts a little bit more clearly, especially since there was somebody absent today. So our initial population is going to be 180 bacteria. And our B is our growth rate, which in this case is 2. And it's 2 not because it says 2 hours, it's 2 because we are doubling. So if we tripled every 2 hours, our growth rate, B, would still be 2. Our T is our time. And it looks like we're going from 9 a.m. to 4 p.m. the next day. So it looks like we're going to have 24 hours. An entire day is going to go by. Plus the distance from 9, or the duration from 9 to 4. So 9 a.m. to 4 p.m., that's going to be 1, 2, 3 hours to noon, 10, 11, 12. And then 1, 2, 3, 4. So that's 7 more hours, plus 7 hours. That's going to give us a time of 31 hours. And D is our period. How long it takes to double or triple or whatever. And that is our 2 hours here. Now, in case you haven't noticed already, certain of these variables are always related. Y and A are always related because they're always they always measure the same kind of quantity. And also, our period and our growth rate, B and D, are also always related. They're always measuring the same, or referring to the same value. So growth rate is about doubling, and this is about how long it takes to double. Okay. Of course, they're all related. Okay, and then we have this general formula. Y is equal to A times B to the power of dt over D. Okay. So I'm going to rewrite this with, so it looks like the t value that we're going to be looking for is 31 hours. So let's call this P of 31. So just to be clear, our general function would be P of t our population depends on the time you leave these bacteria to double. And that would be, take our A value of 180 times our growth rate 2 to the power of t over the period of 2. Great. But in this specific case, we want P of 31 hours. So it's equal to 180 times 2 to the power of 31 divided by 2. All right. So this actually is not a question that involves a lot of algebra. We can just find the value. P of 31 is equal to 180 times 2. But the 2 has been raised to a power, and there's actually a fraction up there. So you can either use your fraction button, or you can use the division. But if you use the division symbol, you're going to have to add some you're going to have to add some brackets. So I'm going to show you how to do it using a fraction button first, and we'll do brackets next time. Okay. So, as you can see, leaving your steak or whatever out on the counter for like a day or something like that is going to very dramatically increase whatever very small amount of bacteria are going to be on that steak, because this is a very large number. It is 1.93, which I'll round, to times 10 to the power of 11, which is to say it's 1.93 times 1 with 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, I draw one too many. Just so we're clear, how big is that? That should be, I think, 100 billion? 100 trillion. No, 100 billion. 100 million. Yeah. So it's 1.93 times 100 billion, or 193 billion bacteria. And that is our final answer. So if you've ever seen a bacterial colony or a little bit of mold spore grow on your leftover food, that's just a bunch of these bacteria all clumping together. There's billions of them all feast on your leftovers. By the way, if you express your answer in scientific notation, that is fine. You do not have to always expand an answer like this. Okay, moving on to question dos. All right, this one looks a little bit heavier. Oh, great, a discussion about the inflation rate. I believe this came up in our discussion this week. So we've got an inflation rate, and that's about 1.7. Inflation rate in Canada is 1.7%. That means that the cost of basic consumer goods increases by about 1.7% from one year to the next. All right, and if we assume that this inflation rate is stable, if the market basket is what we call this, a basket of goods is $1,000, how much will it cost 10 years from now? How much will it cost 10 years from now? And so what else do we know here? 1.7% from one year to the next. That's probably pretty important. It's not over every 10 years or anything like that. And lastly, we know that we have a market basket, that's what it's called, of $1,000. What this means, basket of goods, in case you were wondering, it means that there is a set number of items that are in what's called they call it a market basket. It's like a theoretical basket full of goods that you can buy. And in that basket, there would be things that people typically purchase, like a loaf of bread and a jug of milk and bar of toothpaste and compare that to how much it costs in the next year. And that's how we determine how much our money has depreciated, or in other words, how much it is inflated. Okay, so with that out of the way, let's try and solve this sucker. All right, so again, Mr. Thielman will have drilled into all of you physics students that it's really important to start by just giving values to each of our variables. List what we know. This is the G step in grapes. So our final value, this is going to be our final amount, or this is going to be the value of a market basket of goods in 10 years. So this will be the value of the basket after 10 years, which I can call, I think should I use V for value, C for cost. I guess we use the word cost. So let's say cost after 10 years. So it's going to be a function that's depending, C is a function that depends on t, cost is going to depend on time. Okay. Our initial cost of a market basket is $1,000. Our growth rate, okay, so our growth rate is going to be 1.7% is what a cost of this is going to be from one year to the next. So that means it's going to be the 100% that it costs right now plus that 1.7%. Or really, it's 101.7%. So if we turn that into a decimal, that's going to become 1.017. Okay. Time, how long? Okay, so time, which in this case is 10 years. And our period, how long does it take for it to go up 1.7%? Well, it takes 1 year, from 1 year to the next. So 1 year. All right, so we'll write a formula. And it'll look like this. It'll look like C, it's a function of the time. It's equal to 1,000 times our growth rate, 1.017, to the power of 10 over 1, which is to say 10. Oh, actually, it should have been t over 1. And then cost as a function of 10 years, if we put in an input of 10, that will give us 1,000 times 1.017 to the power of, 10. Okay, so how much will $1,000 worth of typical goods cost in 10 years in Canada, if we assume the inflation rate remains constant? 1,000, a lot of glare there, times 1.017 to the power 10, which is to say they will cost $1,183.62. Cool. All right. So then we can move on to, well, it looks like we have a half-life question next. All right, so we know the half-life of caffeine in Mr. Tang's body is 4 hours. That is a half-life. And when we see half-life, we need to know that that's referring to how long it takes for our value, like of caffeine in this case, to decrease by a factor of 1/2. So our B value is 1/2. And so whenever you see half-life, you want to think that's going to mean, rather than doubling or tripling, we're going to be multiplying the value we have by 1/2. And it's every 4 hours. So Mr. Tang drinks a coffee at 7 a.m. Mr. Tang drinks a coffee at 7 a.m. And a coffee is about 145 milligrams of caffeine plus brown water. Flavorful brown water. Okay. And then he has a bottle of Coke at 11 a.m. That's 55 milligrams of caffeine. How much caffeine will there be in his system at 11 p.m.? That's 55 milligrams. Okay. Well, I think this is an interesting question for several reasons. Okay. So, what's happening here? Can we just add 145 milligrams and 55 milligrams and let that represent our Y value? No. Because by the time Mr. Tang drank his Coke, the caffeine had already started to degrade. So it's actually his profile of caffeine over time is going to look like this. It's going to start at 145 milligrams, not 145 grams, it would certainly kill him. And it would decrease, and then if that's 7 a.m., 11 a.m., it's going to spike, and then start decreasing down like this. So this spike is a problem. However, you might notice that 11 a.m. is exactly 4 hours after 7 a.m. Exactly one half-life. So at 11 a.m., exactly one half-life has occurred. And that's for the coffee, 45 milligrams. So that means at 11 a.m., Mr. Tang has half of 745 milligrams. There is already half of 145 milligrams. So what does that tell us? Half of 145 is 72.5 milligrams. So then, at 11, Mr. Tang gets a spike of caffeine because he drinks a Coca-Cola. And so at 11 a.m., Mr. Tang's caffeine initial would be 72.5 milligrams plus the new amount that he's going to get from his Coca-Cola, which is going to represent, what is it going to become, 127.5. So this is left over from the coffee plus the Coke. Now, say you didn't notice that that was true. So you didn't notice that it was exactly 4 hours between 7 a.m. and 11 a.m. Well, then you would need to calculate the amount of caffeine in Mr. Tang's body from the caffeine at 11 a.m., so starting counting at 7, plus the amount of the amount of caffeine from his Coca-Cola at 11 a.m. and really solve two problems. that actually would be fine. That would be very doable. However, since we can exploit this problem and then start and solve only one problem, if we can exploit the fact that it starts at 4, after 4 hours. Okay, cool. So then let's get on to listing our variables. Our y is our final amount of caffeine in Mr. Tang at 11 a.m. So we'll call that mass as a function of time, which kind of looks like Mr. Tang, MT. A, that's our initial amount. And we're going to start counting at 11 o'clock because we're going to be crafty and exploit this method. Otherwise, we have to do this whole thing twice. Growth rate. Well, we know this is a half-life, so growth rate is going to be 1/2. Time is going to be the amount of time that elapses between 7 a.m. and 11 a.m. and 11 p.m. So that means there's going to be 12 hours. And the doubling time, the period. Oh, I'm sorry, I didn't realize I was writing off of the screen. The period is 4 hours. The half-life of caffeine in a body. Of course, the half-life of caffeine in a coffee or in a Coca-Cola is something entirely different because there's not a bunch of biological machines trying to break it apart inside a coffee. All right, so that means we have m of t is equal to 127.5 times a half raised to the pardon me, I knew that was coming. To the power of t over d, t over 4, and in this case our time is 12 hours. So I'm going to substitute that straight in. So we're really looking for the mass of caffeine after 12 hours. That's equal to 127.5 times a half power of 12 over 4. And that's really 3, right? So m of 12 is equal to 127.5 milligrams times a half to the power of 3. And a half to the power of 3 is an eighth, so it's really an eighth of 127.5, but I don't need to even do that much thinking. Times, I'll write it in as 0.5 to the power of 3. 15.9 milligrams. So the mass after 12 hours is 15.9 milligrams of caffeine. Sneaky question. All right. Last question. So, polluted water is passed through a series of filters. Each filter removes 85% of the remaining impurities. Initially, untreated water contains impurities at a level of 442 parts per million. Okay, or ppm. So we're going to find a formula for L, the remaining level of impurities after the water passes through N filters. Okay, so it looks like we're only looking to find a formula after it's passed through N filters. All right, So let's see if we can sort this out. Question 4. Our y value is going to be our remaining level of impurities after n filters. So we'll call that L as a function of n, the number of filters. A is our initial amount of impurities. I didn't highlight the word initially, but that would make it an initial value. So that means we're at 442 ppm. We're just going to treat ppm, parts per million, like a unit. So we're not going to, just because there's a number in this unit, million, doesn't mean we have to turn this into some decimal. Although you could if you wanted. All right, our growth rate, our rate. So if we remove 85% every time, so that means if you had 100%, after one run, you would have 15%, because you removed 85%. So that subtracts 85%. And the question is, and so if we did that again, we would also remove 85% of 15%. Now the question is, what am I really multiplying by to get to 15%? I'm multiplying by 0.15. So that's how I would get the amount of effluent after another run, if I was curious. It'd be 15 times 0.15, which would be 2.25%. And then after the next one, 0.15 times 0.15 would be 0.3357, or 75%. And that would be another times by 0.15. And we can keep going if we want to, arbitrarily. So that means our rate, growth rate, is 0.15. Our time, T is actually the number of filters. So rather than a certain amount of time, we're just going to express it as a number of filters, the number of times this process repeats. So we're going to call that N. And our D is, well, I guess we have, we're not really talking about a period in this case, so we're actually going to call it 1. That's actually like the example with the paper folding that we talked about earlier today. So D is not relevant. Our period is not a factor. Okay, so we can express this as L of n is going to be equal to 442 times 0.15 to the power of n over 1, which is just n. And that is our final answer. That's all we need to do. Let's just make sure it works. We can test this if it works, because we just crunched some numbers, how much effluent there would be after you took away 85% each time. And so after two, what do we call it? 2 filters, we should have 2.25%. So let's imagine n is 2. Let's plug that in. 442 times 0.15 to the power of 2. Oh, it didn't work. Oh, right, because we were starting with 100%. Stupid me. So actually that, okay, I see. If we divide that by 4.42, yeah, we get 2.25. Okay, sorry. That was a bad example. All right, great. Well, that's it. Let me know if you have any questions about any of those. and we'll see you over the weekend. After the weekend.